Thank you for your introduction. I'm very pleased to introduce our study titled "The Crick Effect on Geometrically Nonlinear Behavior of Microstructured Composite as a Nonlocal Continua." My name is Farui. This presentation includes the following sections. The first is the introduction of the motivation of the study. As well as the presence of the crick can play an important role on the mechanical behavior of many materials, including the microstructured components. Especially, most of the components can have a geometric nonlinear and behavior under applied load. The classical continuum cannot accurately describe the mechanical behavior of the such components. So a nonlocal continuum is needed to give a satisfactory result for such a component in which the internal length has a prominent role. The nonlocal here means scalar-dependent continuum with dispersive properties in wave propagations. Here, we use the Cosserat continuum as well. This continuum introduces an additional degree of freedom, that is macro rotation. So this continuum can be an implicit nonlocal continuum. Here we show the linear elastic constitutive equation for this continuum as well as its compact form. We can see that the couple stresses and the curvatures also involved in this equation. Next, we will consider the geometric nonlinearity for this continuum with a total Lagrange FEM formulation to take some nonlinear simulation. In the simulation section, we take the classical cantilever beam problem as a example. This beam has a crack of which location is referred as the parameter x. We consider this beam is a composite material which is made of hexagonal blocks interacting with each other by the interface. Each blocks can be formed according to their geometric parameters as shown here. Sorry. Next, we will select 3 special hexagonal patterns termed the regular, hourglass, and the skew by changing the parameter alpha 2 and alpha 3. By using some blocks RVE and according to a homogenization process according to this literature, we can get the constitutive matrix for this RVE under different scalars. We can see that the scalar have an effect on the D and the B matrix of the constitutive and does not affect on the A matrix. This is a result for the vertical displacements U2 for all study cases in the deformed configuration. We can see that there is a scalar effect on the result of the Cosserat continuum. As the scalar decreases, the result is more close to the that of the Cauchy continuum. Different composite materials also show different nonlinear behavior because of their various constitutive matrix. Here we show the deflection at the point 3 of the beam. We can see that there are very clear nonlinear behavior for both two continuum, and the Cauchy continuum shows the highest deflection, and followed by the Cosserat continuum with the scalar effect. Here we show the crack effect on the deflection at the point 3. We adapt a cracked beam and a perfect beam without crack. We can see that the deflection from the cracked beam is greater than the deflection from the perfect beam for the both two continuum. As the introduction of the crack stress concentration can be observed at the tip of the crack. We can also see that the stress concentration for all the study case also showing the scalar effects for the Cosserat continuum, and also the Cauchy continuum shows the highest stress concentration at the tip. This is the result of the horizontal stress at the P4, the crack tip P4 as a function of the load. Also, the nonlinear behavior can be observed, and the Cauchy continuum shows the highest stress concentration. And as the scalar increases, the stress concentration for the Cosserat continuum decreases, which indicates that the Cosserat continuum has a function of a redistribution of the stress. Also, we show the crack effect on the horizontal stress at the crack tip P4. We can see that as the introduction of the crack, there is a clear stress concentration can be observed at the P4. However, the crack does not significant effect on the P1 and the P2 as shown here for the both two continuum. We also present the effect of the crack position on the deflection and at the P3. The location of the crack is referred by the parameter x. We can see that the x, as the x decreases, the deflection become more bigger, and that would be more clear for the effect of the crack position on the horizontal stress at the P4. We can see that as the location of the crack more far away from the load applied location, also the x decreases, the stress concentration at the tip become more clear, more significant. And finally, it is the conclusions and some remarks. Because of the time limited, I will skip this slide. And finally, thank you for your attention.